So let's talk about climate change. I mean, this is a very sort of not 100% tongue-in-cheek, but somewhat in terms of the impacts as the temperature increases on our planet. And you can see that we've already raised the temperature by approximately 1.1 degrees since pre-industrial times, and we're on a pathway for much, much higher temperatures, and the impact of that is potentially quite severe. So let's start with the science. We think of our atmosphere as really an unending expanse. It seems to go up forever, but if you view it from space, the atmosphere is actually a very thin veneer around the edge of the planet. In fact, if I had a globe at scale here in my hands, the atmosphere would have the thickness of a piece of paper around that. So it actually is quite thin. And into that thin atmosphere, we're dumping today around 110 million tons of global warming pollution, these greenhouse gases, on a daily basis, about 37 billion tons per annum. And that has increased dramatically, even just in the last 50 years. Why is that important? Well, our planet maintains its attractive temperature by the energy from the sun. A lot of that is reflected, but some of that infrared or heat is trapped in the greenhouse gases. And as you can see from this graphic, as the concentration of CO2 increases in the atmosphere, as it is now, more heat is trapped. This is not under a denial by anyone. This is a very well understood chemical process, physics and chemistry, and therefore more heat is trapped as the concentration of carbon dioxide increases. There are many, many sources of carbon dioxide, and indeed this and other greenhouse gases, this is part of why this is such a huge problem to overcome. Everything you touch, everywhere you turn, has a carbon footprint. In other words, there's some emanation of greenhouse gases from that, and you can see a myriad of these sources on this slide. But by far, the largest source of these gases, of carbon dioxide in particular, which is the largest warming gas, is burning fossil fuels. So coal, gas, and oil, these three fossil fuels, which have been locked up in the planet for millions of years, are being dug out of the ground and burned. That has resulted in a large increase in the concentration of carbon dioxide in the atmosphere. So you can see this graph is quite famous. It's called the Keeling curve. Charles David Keeling began measuring the concentration of CO2 in the planet's atmosphere in 1958, and at the time it was around 280 parts per million. Today, that has risen to 415 parts per million. That's a 50% increase in CO2 concentration in really only 60 years. Interestingly, you can see the curve exhibits a seasonal variation. That is the large forests in the northern hemisphere. In the spring, when the forests bloom, they suck a huge amount of carbon dioxide. Of course, trees and forests are one of our nature's big carbon sinks. They suck in carbon dioxide. And then in the fall, when the leaves come off the trees, there's a release of carbon dioxide. So we have this sort of the world is breathing out and breathing in once a year. Quite interesting. But we see this big climb in CO2 concentration over time. Now, why is that concerning? If we take ice core data from Greenland and Antarctica, we can drill those cores up to 1 kilometer deep, pull them up, and slice them open. And in the air bubbles trapped in those deep ice cores, we can date and build a history of both temperature and carbon dioxide historically. And you can see this data series goes back more than 800,000 years. What you can also see is that there seems to be a large correlation between high levels of carbon dioxide in the atmosphere and high temperature levels. Now, remember, we have a working hypothesis. What do I mean? We know that carbon dioxide traps heat. So we would suspect that when you saw a peak in carbon dioxide, perhaps you would see a peak in temperature. And indeed, if you look at this graph, that is exactly what we see. So it confirms that hypothesis. And you can see that historically on carbon dioxide, the blue line, we've never really gone above 290 parts per million. And each of these periods where it goes to a low, then a high, is a glacial and an interglacial period. So this last dip, most recent dip at the low point, that was the last glacial period, approximately 17,000 years ago. And just to give you an example of how severe these moves are, the New York City was covered in approximately 2 kilometers of ice at that first low point. So these highs and lows have dramatic implications for the planet. Unfortunately, in only not thousands of years, in a very short period of time, this is where we have taken the concentration. So these processes normally are on the 100,000 year type cycles, but we've in only 60 years massively blown out. And again, when you just look at that, you realize we're running an experiment now on the planet that actually not even the best climate scientists know the results of. But even more worrying is where we're headed. If we do not get a handle on this issue and we continue to generate this 38 billion tons of CO2 per year, we are likely to increase this dramatically with even more dramatic implications for the planet. Now, with this high concentration of CO2, we know it traps heat. We should be seeing hotter temperatures. And indeed, if we look at the data, we are. We're seeing a large departure from average temperature. We're seeing that 19 of the last 20 years have been the hottest years on record. Last year was the second hottest year on record, and that means the last 5 years are the 5 hottest years on record. If you work in asset management, then you understand that when the risk lies really in the tail of a distribution, not really in the mean. So what I'd like to illustrate where the risk lies here in temperature by showing you a baseline from 1951 to 1980 on temperature. And the blue are colder than normal, average temperature, and hotter than normal. If we use that as a baseline and then we move in decadal jumps, you can see what happens to the tails. So the first decade is from 83 to 93. And you can see on the right here now we have a very small tail of very, very hot days. The next decade, it shifts again, and we have a larger tail. And finally, the last decade, which only goes to 2015. So mind you, we're still missing some of the hottest years, and yet we have now 14.5% of these days are extremely hot days. This is where the risk lies to our economies, to water scarcity, to drought, etc. We experienced some of this in the past summer. Here in Europe, we had a heat wave with temperatures above 45 degrees, 45 C. I mean, at these levels, infrastructure, even road and rail, if they're exposed to this for extended periods, begin to break down. Temperature phenomenon is not localized. This is 2018. There were 224 all-time temperature records set. Most of those, I'm sorry to tell you, were broken in 2019, last year with the heat waves. I just have not had time to update the data. Now, the single biggest impact of higher temperature, the easiest one to forecast, the climate system, as we know, is probably the most complex system on the planet. And therefore, forecasting into the future is difficult. But the easiest thing to forecast is the impact of a higher temperature on the hydrological cycle. Now, we understand how the cycle works: evaporation, precipitation, and then it flows back to the sea and repeats. If you have higher temperature, again, pure chemistry and physics, we get more evaporation. That's well understood. What isn't as well understood is that with every 1 degree temperature increase, the capacity for the atmosphere to hold more water vapor, more rain, increases by 7%. That can result in substantial amounts of precipitation, and we're seeing this now present itself in flooding. Globally, these precipitation anomalies are increasing, and they will continue to increase as we continue to increase the concentration of CO2 in the atmosphere. One follows the other. But that same heat that evaporates our lakes and oceans draws moisture from the land, and that has severe implications for drought, water scarcity, and crop production. So in Brazil, this is causing quite large, much more frequent droughts. And as David Sobel says at Stanford, there is an under-recognition of how sensitive crops are to heat. And this heat exposure is increasing dramatically. In fact, research calculates that for every day above 29 C, you get a 0.5 to 1% drop in corn yields. And by the end of the century, just looking at the US, you could have corn yields down 1/3 from heat stress. I mean, there's a famous quote from Aristotle who said, the difference between a society that's barbarism and a civil, stable society is 6 inches of topsoil and rain. And this is a very good understanding, because our fundamentally our societies are built upon this need for a stable supply of food and crops. Flooding, water scarcity, and drought. The military are very, very aware of this, and they're often in attendance at climate change conferences that I've been at. Here they say that it's a threat maximizer, magnifier. It's not the only factor in a conflict, but it can be a real factor in increasing the risk of a conflict.